Let's talk about the ways in which streams flow. In physics, there's two types of flow. There's something where one layer is flowing over another layer, and that's called laminar flow. And laminar flow is shown on the top here. Laminar is L-A-M-I-N-A-R. Like if you laminate something, you seal it in flat layers. And the other type of flow is called turbulent flow. And with turbulent flow, a particle of water is not traveling in a straight line down the river. It's getting all mixed up as it goes in that direction there. So it might be higher in the river, then lower, and so forth as it travels down the river. Turbulent flow much better represents the way in which water flows within a stream or a river. Another thing to remember about stream flow is there's going to be some drag or some resistance to that flow based on the actual channel that the stream is flowing in. So here we have two different channels here. One is very wide and shallow, and we can see that what they're showing with the different shades of blue here is where the velocity is at its maximum. And so the velocity is at its maximum here, not right at the bottom of the river, it's near the top of the river because there's not nearly as much resistance from air as there is from the rugged rocks in the bottom of the river channel provides to the river. So the maximum flow velocity would be in the center of the river, and in this case, and then it would the velocity would die off as you move away in any direction towards that and towards the channel of the river, which is shown in brown here. This is not a very efficient flow because there's a lot of water that's being dragged along right at the bottom of this river channel and the sides of this river channel here. The most efficient type of flow would be in a river channel that's half of a circle, kind of like half of a pipe. Once again, the maximum velocity would be just under the surface, right where that air resistance goes away and the water can flow its fastest. And it would have the most resistance and have the slowest flow along the edge of the channel here, which in this case looks almost like a half circle. We can compare the resistance to flow or how efficient the flow is by looking at the ratio between the cross-sectional area, which would be shown in the front of this block diagram here, and the perimeter. If we measure the distance along where the channel meets the water, that would be what we're talking about by the perimeter or the wetted perimeter. And if we measure those two, then we can compare those and see where the most efficient flow is. Another way that we measure flow is by the discharge of the river, and that's the volume of water that's moving through any part of the river over a particular time. And in small areas here, not if we're going from the beginning of the Mississippi to the end of the Mississippi, but if we're just looking for a little stretch of river like this, we can say that the discharge of this river is going to be equal. So the volume of water moving through this area here is going to be the same as the volume of water moving through this area here per given time, and the same here, because it just you can't back up water like that, right? It's just going to naturally flow. The way that we calculate discharge, which is sometimes measured as Q, is we multiply the cross-sectional area, and here we see kind of a cutaway of what the cross-sectional area might look like, and we multiply that by the velocity. So immediately here we can see that the cross-sectional area is much larger here in this pool than it is in these two rapids. And because the cross-sectional area is going up, and the discharge has to stay the same, we know then that the velocity of the water is going to go down. And of course, this is just what we see in nature. Rocks move very quickly when they go through a confined area like this, a canyon, or over a steep slope. And then they move much more slowly when they're in a pool, an open area where there's not much of a change in elevation from one end to the other. So this once again is called the discharge of the river, and it stays constant over small areas as long as no tributaries are entering into it. And of course, we could just estimate the cross-sectional area, or we can make very detailed measurements of the cross-sectional area, or make sure all of the water goes through one particular area here. And we do this in part by these things called stream gauges, G-A-G-E-S. And here we can measure how deep the water is, and we can also, in some cases, have a good feeling for what the bottom of the stream channel looks like, so we can very precisely calculate the cross-sectional area of water moving through this location at any particular time. We have these all over the United States because they're good indicators. If there's a potential for flood, we can use stream gauges in order to measure what the discharge, how much volume of water is going to be flowing through any particular area at a given time.